We want to talk about motor dynamics, or better, we want to talk about the dynamics of mechanical systems. So we did steady state operation, and now we want to find out, well, what happens as we kind of ramp up. So let's go look at this video about why we care about dynamics.
Now I'm just going to launch it. So I put it in sport, insane mode, and then you just hit it.
Whoa!
And that's 60. So you don't expect it, right? Isn't that neat?
That's awesome!
I'm really mad that the option is insane. Like, it's not like just...
Boy, that's perfect. Isn't that good?
That's a random, like... What's the
Because
feature?
the car is insane, right? Everyone thinks the car is insane, so why not have, you know, like an insane mode, right?
That makes sense.
So you just come to like a complete stop,
All right.
and then before you know it, you just jam on
Oh,
it.
bro! What the fuck?
That's 70 miles an hour.
Okay, so now that we're back looking at this, we want to look at what are some of the equations and the dynamics related to this type of acceleration. So we have a torque. We understand the torque force relationship that we had before, and we have equations now of torque versus angular acceleration, and then we want to relate those to rotation speed, and then you have to solve a differential equation to get it to work out. So let's look at some of the basic equations. So first of all, like we have done before, we have our torque equation, which was related to our applied force and the distance away from the rotation axis. Now we have our angular acceleration equation, which is angular acceleration is the rate of change of our angular speed with respect to time. In order to do this, we are going to use the concept of the moment of inertia. So then we have the sum of the net torque is equal to the moment of inertia times the acceleration. So this is going to be related to our force equation that we had before in physics. So before, this is similar to the sum of the forces is equal to mass times acceleration. So you see we've changed from this linear acceleration into angular acceleration, from mass into moment of inertia. So let's look a little bit about this, okay? So let's go look at an example of a fan. So notice the fan starts rotating really slow, and then as time goes on, it rotates faster and faster as the fan starts to accelerate. This is a big fan for a wind tunnel, so it takes some time for it to speed up. So here are the equations for our fan. We basically have the moment of inertia, and we have the acceleration, and it's equal to our net torque. So we have two torques. We have the torque of the motor, and then we have the torque of the fan. So let's go look at this in a little bit more detail. Here are our plots. So let's start in the beginning. So right here in the beginning, you see this black one is our motor torque, the blue one is our speed, and the red one is our fan torque. You can see right here. So initially we apply our voltage, and there's no torque from our load because our fan isn't moving because it has a quadratic force speed plot. And then we see that our motor current is starting to increase. And as our motor current increases, then our torque increases. So as this starts to go up, and so this right here, when we're kind of speeding up, this is the inductance of my motor. So the inductance of my motor causes it to start speeding up. But once I'm up in these ranges up here, you see that my torque of my motor is larger than my torque of my load. So therefore, I'm going to start accelerating. So now my motor is going to start rotating. Okay, and as my fan starts rotating, you know, it's still fairly small because we're going to zoom in, but my fan torque is going to start increasing as my motor starts rotating. At the same time, the motor rotating is going to cause the torque of my motor to come down, because remember that we have a linear torque speed plot for the motor. So as my speed starts to increase, my motor torque is coming down, my fan torque is going up. Okay, so let's zoom out a little bit more. So now when we kind of zoom out, you see we're at the peak. This is my inductance we had before. Now my speed is increasing, so my motor torque is decreasing, and my fan torque is starting to increase. Okay, and so then the rate of this increase in my speed is going to get smaller and smaller because my net torque is going down. Eventually, you get to some point here where the torque of the motor and the torque of the fan are equal, and then you see that the speed of my fan flattens off because now that the net torque is zero, if my net torque is zero, there's no more acceleration, and all I have is the speed. So you can kind of see this is the dynamic. So the bigger that the black one is over the red one, the more acceleration I have. And so as we're getting closer and closer, you see right in here, I'm getting less and less acceleration until they're equal, and then my acceleration goes to zero, and my fan's at the constant speed. Okay, let's go back here and look at some more examples. So this was our fan example. Now we want to talk a little bit about moment of inertia. Okay, so we want to look at the list of the moment of inertia. So we have points. We don't really care about points. We have bars. If I wanted to do a fan, I would break a fan up into rotating bars. Typically, we would do this one for the fan. We also have thin disks, and so you see it as a moment of inertia that's based on the mass and the radius in 1/2. We have tubes or cylinders, and then we have solid cylinders. Okay, so the ones that we use the most are the solid cylinder and the tube most of the time. Okay, so let's start by just looking at a motor. So the motor itself has a moment of inertia. So the motor rotor is basically a big chunk of metal. So it has the approximate length of the rotor, and it has a diameter, and it has a density. So we calculate the total mass, and then we do 1/2 r squared. So here is our mass. Here is the radius squared of my motor, and here's the 1/2. And so then we calculate this is the moment of inertia of the rotor motor. Now let's look at a box, a weight, and a pulley system. So weight and a pulley system, you see all of this weight is getting applied at the edge of the pulley. So because of that, we are using this is basically going to be the equation of the cylinder because all of my weight is at a distance. So I use J equals mr squared rather than the 1/2. So the 1/2 mr squared is if it's a solid cylinder, and this one is if all of my weight is applied at the radius point. And so then this would be my moment of inertia for a weight and a pulley system. Okay, well, let's say we have a treadmill. So in a treadmill, I have a belt going around a wheel that's being driven by a motor. So you see that the weight and the belt, okay, are all being applied at the same radius. It doesn't really matter if it's going around here or it's going all the way around there. So what we see here in this example, we have the belt and then we have the roller diameter. So this is the roller right here. And then typically they have a flyweight. And so that just makes a big solid cylinder here so that once it gets going, it kind of maintains its weight. And then it has the motor and the person. So if I look at these right here, we're going to take the belt, the roller, and the person, and they all apply the force at the radius of the cylinder. So they're going to use the mr squared. The flywheel is a solid disc, and so it's going to use the 1/2. Okay, so we're going to do a simple example of a treadmill. So we have our treadmill that we're trying to get up to a speed of 7-minute miles. So this is a nice fast run speed for the runners out there. And I don't want to wait around because I'm so busy. So I want the treadmill to be able to get up to a speed, this running speed, in 3 seconds. So we're going to be using a motor with a current limit. So this means that the motor is going to put out a constant torque rather than a torque that varies with speed. This is kind of practical for a lot of motors when they're, you don't want them to overheat, and it makes the math a little bit easier. So we can do this simple calculation. And then we're going to assume that all of the friction is in rolling friction, which is independent of speed. So we're going to assume that the treadmill has a rolling friction of 0.001 times the mg, times the mass, times the gravity constant. And we're trying to calculate what is the motor torque. So the first thing that we have to do is we have to convert it from miles per minute type speed into meters per second. So here is my conversion between miles per minute into meters per second. And then we have to convert our linear speed into angular speed. Here's the math here. We're basically taking the linear velocity divided by the radius to get what my angular speed needs to be for the motor. So we need to get this rotating system, the motor, up to 50.3 radians per second. Okay, so here's our basic equation. So our basic equation that we had before is the net torque is going to be equal to the moment of inertia times the angular acceleration, which is right here. So our net torque is going to be the motor torque minus this friction torque. So we're going to plug in, here is our total weight, and so we're trying to get the total motor torque minus 0.83 is our net torque. We're going to use the moment of inertia that we calculated earlier, which is 0.517 kilograms meters squared. Okay, so now we're going to go to our torque equation up here. Okay, and so we're trying to figure out what do we want the acceleration to be, because if I have the acceleration, then I can get the net torque. So I'm trying to get up to a speed of 50.3 radians per second, which is going to be equal to my acceleration times my time. And remember, my acceleration is constant because I'm using a current limited DC motor. So my net torque is going to be equal to J times my alpha. So I'm going to take my J from here, and I'm going to take my acceleration from here and plug them together. So I get a net torque of 8.67 Newton meters. Well, my motor torque is going to have to be 0.83 higher than that because of my loss, you see right here. So I need my motor to put out 9.5 Newton meters of torque. So let's go look at our motor. So we're going to look at this 726 motor, and we see, and it has an A, B, or C configuration. We're going to use the A configuration. Okay, so here is my torque constant, and this is in centimeters. Okay, Newton centimeters instead of Newton meters, converted into that, and this is going to become 0.15. I have a resistance of 0.4, and it has a peak current of 75. It has a inductance. We're not really going to worry about the inductance for this simple problem. We're going to assume that our mechanics is going to dominate our speed. Okay, so we have the 0.15 and the 0.4. So let's go back. Okay, so we're using a coefficient of 0.15 and a resistance of 0.4. So starting out, we have omega equal to 0. So our current is going to be equal to the 9.5, which is our torque, divided by our torque constant. So we're going to need 63.3 amps, which is less than the maximum current of whatever it was, 75 amps or whatever. So the motor isn't going to burn out when we're starting up. And so we have to apply a voltage of the current times the RA. So we have to apply a 25.3 volts to our motor. At the maximum speed, my omega goes up to 50.3. So then you see that my current is going to be equal to, again, the same 63.3 that we had before, but now I have this back EMF. So to compensate for the back EMF, I have to increase my voltage. So between starting and my maximum speed, I'm going to be linearly increasing the applied voltage from 25.3 volts up to 32.8 volts to stay in this constant current regime. Okay, once I reach maximum speed, I want to stop accelerating. So then I want my net force to go to 0. So I want to be applying 0.83 Newton meters so that my net force, this just equals the friction to keep it going. So in order to maintain the speed, I am going to put in the 0.83 divided by the 0.15. So I need to be putting out 5.5 amps. And so using this same equation here, I'm going to change my voltage from 32.8 volts down to 9.7 volts to get it all so that it stays at the same speed. And that is my dynamic equation example.